Hello everyone, I am Shiddartha. I am a PhD student at the University of Alabama. Today I am going to present my research on T91 iron, chromium and silicon multimetallic layered composite for nuclear fuel cladding application. So the critical challenge in Generation 4 nuclear reactor design is to develop new low cost material that can retain their structural integrity under harsh condition at the reactor environment, and they should retain their integrity, structural integrity, for a very long period of time, probably 60 more than 60 years. However, developing new material for nuclear structural application requires numerous tests for establishing the ASME code for themselves. Uh, so in this case, the MMLC can provide us a solution by decoupling the interaction between different established alloys through forming a functional graded material. In that way, we can actually use the existing ASME code for those particular alloys for the entire structure, which can be applied to the actually entire structure. Also, the alloys that we have used for this particular MMLC is iron, chromium, silicon, and T91. They actually have very lower oxidation tendency that actually helps them to retain their structural integrity at harsh condition without any corrosion. And that's why this particular MMLC is very much promising for the accident tolerant fuel cladding research, and their lower oxidation tendency actually minimize the risk of the accident during the loss of the coolant condition in a nuclear reactor. For the safe operation of the molten salt reactor, it is very much important to choose the appropriate material for fuel cladding. Recently, ferritic martensitic alloys are becoming very prime candidate for nuclear fuel cladding, as they have very high defect recombination rate and superior structural strength. In this study, we have investigated T91 iron, chromium, silicon MMLC composite because iron, chromium, silicon and T91 has a lower oxidation tendency, and they have very high resistance to the corrosion at a very extreme condition. Conventional zirconium alloy that have a very higher oxidation tendency that has been used for decades in nuclear fuel cladding application, that can actually lead to the reactor to produce a vast amount of hydrogen, and that vast amount of hydrogen can be trapped into the reactor chamber, and at the very extreme condition like loss of coolant condition in the reactor, it can actually act as a hydrogen bomb and can produce a devastating accident that happened in Fukushima back in 2011. Also, the radiation induced defects can deteriorate the dimensional stability and the structural strength of the material. So that's why we have also studied the defect formation behavior for those particular T91 iron, chromium, silicon MMLCs. We have investigated T91 iron, chromium multimetallic layered composite with different primary knock-on atom energy. We wanted to see how the primary knock-on atom energy actually affects the radiation damage of this particular material. We used atomistic cascade simulation for modeling the radiation damage in this particular case. We have used ZBL modified EM potential to define the interatomic interaction, and this ZBL modification actually creates ZBL modification actually enables the potential to define the high energy cascade solution. We have introduced primary knock-on atom energy with varying energy ranges from 10 keV to 100 keV at 1000 Kelvin temperature. We used successive cascade algorithm to reach up to a radiation dose level of 1 DPA. Here the DPA is the displacement per atom, which is a measuring factor for the radiation dose. For reaching to that particular DPA level, we had to introduce around 500 primary knock-on atom into the structure. In the figure we can see how the sharp T91 iron chromium silicon interface get thicker upon the introduction of the radiation dose. We can also see the energy cascade formation behavior upon the increment of the radiation dose for this particular T91 and iron chromium silicon MLC. So we have used the stream calculation to determine the DPA per primary knock-on atom. Actually, what the primary knock-on atom does, it actually displaces the neighboring atom, which actually results in an atomic displacement cascade. To evaluate the radiation damage, the DPA or the displacement per primary knock-on atom is a fundamental parameter that actually characterizes the lattice displacement events. For determining the DPA per primary knock-on atom, we have used the same structures and simulation setting in the stream that we have used in our molecular dynamic simulation. So the calculated value we got for different primary knock-on atom energy has been shown in the figure E, and we can see it's kind of they actually have kind of linear relationship with the primary knock-on atom, and for the lowest primary knock-on atom energy we got 0.0015, and for the highest it was 0.00271. So in the figure we can see a linear increasing trend of radiation enhanced diffusion coefficient with the radiation dose. To exclude the thermally activated cell diffusion coefficient, we recorded the radiation enhanced diffusion coefficient at the very beginning of the thermal spike region, and we got the radiation induced diffusion coefficient at a range of 10 to the power minus 9 to 10 to the power minus 8 meter square per second, which is actually higher than the thermal diffusion coefficient. We can also see the radiation induced diffusion coefficient decreases as the primary knock-on atom increases. So they have actually pretty much inverse relationship in this case. So in this figure, the mean square displacement has been presented for 10 keV and 100 keV energy. So observing those two particular figure, we can see the mean square displacement at the TS region or the thermal spike region is kind of same. But at the ballistic phase of the cascade simulation, the mean square displacement is kind of increasing slowly for the 100 kV 100 kV primary knock-on atom energy, and for the 10 kV primary knock-on atom energy case, the mean square displacement actually decreasing. So that's why you have seen an inverse relationship of the radiation enhanced diffusion with the primary knock-on atom energy and in the earlier slide. So in the earlier slide we have seen from the structural evaluation that the interface actually get thicker, the sharp interface get actually thicker. So here in this figure of this slide show support this visual analyzation with the quantitative representation of the interface thickness as a function of the radiation dose. We can see the radiation dose increases, the interfacial thickness also increases kind of linearly at the very initial DPA, but after 0.2 DPA the interface thickness actually it actually gets saturated. So that's why the curve actually gets flattened in this case. So here in the figure shows the number of the Frankel pairs as a function of the radiation dose, and the Frankel pairs was higher initially at the lower radiation dose, but as the radiation dose increases and it goes beyond the 0.5 dPa, the Frankel pairs formation actually decreases, and at very high radiation doses the defect formation doesn't change with the radiation dose increment. So in the figure we can also see the number of the radiation and the number of the defect actually decreases as the primary knock-on atom energy increases. The common neighbor analysis of the structure has shown the structural rearrangement of the iron chromium, silicon chromium, and chromium molybdenum and molybdenum neighboring atoms after implementing the certain amount of the radiation dose. The structural rearrangement of the chromium and its neighboring atoms in this particular MMLC interface actually suppress the defect formation and the interface thickness at higher radiation dose, because at the higher radiation dose actually this particular rearrangement happens. So that's why we have seen that the interface thickness and defect formation becomes saturated at the radiation dose decreases beyond point 2 dpa. So these are the conclusions that we have got from our investigation. So increasing radiation dose actually uh, widen the sharp interface of the MMLC because of the formation of the defects and the interstitial, and those defects and interstitial actually diffuses through the interface from the T91 side to iron chromium silicon side. And we have also seen that diffusion coefficient and interfacial thickness, mean square displacement actually have a linear trend with a linear proportional relationship with the radiation dose, but the diffusion coefficient and the interfacial thickness have an inverse relationship with the primary knock-on atom energy. And we have also seen the defect for the primary knock-on atom energy become plateau when the radiation dose goes beyond the point 2 dpa. And we have seen that after point 2 dpa there is some kind of phase formation or the phase transformation of the chromium and the neighboring atom and and its neighboring atoms. So that's why it forms some new phases that actually suppress the defect formation and the interfacial and widening of the interfacial thickness. So thank you everyone for listening my presentation. I hope you enjoy the rest of the day.